this afternoon we've got a talk by Nikolay Malkin now, and then a poster session after coffee. Over to you.
Right, thank you. It's nice to have a chance to present a second time to you. This time less didactic, more of my own work. So I should say that I have no right to be here because I'm not really a statistician. I don't work on Bayesian experiment design, but I work on learning-based inference, and in fact I came to the field of diffusion modeling originally by working on sampling through learned sequential decision-making. And it'll become clear how the point of view of reinforcement learning for sampling in discrete spaces led to some of the ideas that I'll tell you about. So here's the plan of what I want to cover. So first it'll be a survey or small crash course in sampling with learned diffusions, also known as diffusion models without data. In fact, sometimes when I present this to a less mathematical audience, I give a little bit of a hyped title to this whole thing and call it diffusion without data. And we'll look at this in the continuous time case. We'll talk about stochastic differential equations and how they can be trained to sample an unnormalized density and what that's connected to. And then we'll talk about how to take this to discrete time and how to make this into an RL problem. So we'll briefly review entropy regularized RL and see how it can be used to solve hierarchical variational inference problems, and specifically the case of learning and diffusion. Then we'll go back, well, after talking about some of the advantages of the RL approach, we'll go back to the continuous case and we'll see how the two are related through the limiting properties. And then with as much time as we have left, we'll see some more cats, some large-scale applications. And we'll finish. Good. So, because I'm talking about both my own work and others, I've color-coded the references. The blue is to everyone who's inspired me. The red is for everyone I've been fortunate to work with. In particular, these collaborators with whom I did some of the primary references that this will be based on. Let's get started then. Right, so on Monday we talked about how to train a diffusion model to maximize likelihood of a data set. So we treat a diffusion model as a hierarchical latent variable model, and we sample the chain of latents starting at a data point, and then we maximize log likelihood in reverse. So effectively this minimizes the KL divergence between two factorizations of the same joint distribution over the latents. So two distributions over trajectories. So just like to continue the example from Monday, if this is our data set in 2D, we have the backward trajectory starting from the data, which we can sample tractably just by adding noise, and we have the forward trajectory starting at noise. And we want to make the two distributions over trajectories equal. If they're equal, then we sample trajectories forward from noise, and we should end up back at the points of the data set. Just a small note before we continue, this will come up. Often in the diffusion model literature, the forward process is the one that noises, and the backward or reverse denoises. But when we talk about sampling the diffusions, as we will, when we generate, we go forward in time. So forward is generative, backward is noisy. So we match these two distributions over trajectories. Now, if we think about this in continuous time, then the trajectories are actually paths in continuous time, so functions from the time interval, say 0, 1, to the space in which our points live. So these are really stochastic differential equations, so stochastic processes, but you can interpret them as distributions over a space of continuous functions. We won't go into such maths here, but just think of the diffusion model as defining a distribution over continuous curves. So, as we just said, diffusion models that are trained given a data set are minimizing the scale divergence between starting at the target distribution and following the backward or noising process, and following the denoising or forward process, which is parameterized by our score-based or denoising model, some parameter state. It's a neural net. So what if we only have the density of the distribution we want to sample, but can't draw samples from it directly? So in other words, we're trying to sample something like a Bayesian posterior, where we can query for the joint by evaluating it in a different factorization, and we want to sample from the density that's proportional to this joint. So this is the problem of Bayesian inference. And when we train a diffusion model to sample a density, as we aim to do, we end up obtaining a model which can be used to draw samples in then infinite time, or be used as a proposal to do Monte Carlo and get approximate samples. So what do we do then? And also, how do we solve the related problem, which I briefly mentioned last time? The related problem of taking a diffusion model prior and multiplying it by likelihood and sampling the posterior. Those two problems are mathematically very similar. So where do such problems come up? Well, beyond the obvious Bayesian posterior sampling ones, in molecular dynamics, we want to sample Boltzmann densities of energies of molecular conformations. In discrete spaces, we frequently want to sample Bayesian posteriors over some structured objects. Here's a work on phylogenetic trees. And there's a multimodal posterior over the ancestral tree of species given the aligned genome data. And as we'll come back to a few times during the talk, many of the methods used in continuous space diffusion can be used just as well in discrete spaces where you can define a destruction process, say one that takes a phylogenetic tree and tears off the root of one of the subtrees one at a time. And the product of the diffusion prior and the constraint, well, I showed this picture on Monday. This is the problem that's intractable to solve, so taking an unconditional model and multiplying it with a constraint and sampling the posterior. Intractable to solve unless we have classifiers trained on noisy data. So this is what we'd like to solve by training a new diffusion model to sample this posterior distribution. So there are a few ways we can do that. I'll take you quickly through a few of them. So one natural idea is to just reverse that KL divergence between two distributions over trajectories, or joints over all the latent variables. So we can't tractably sample the target distribution anymore. But we can sample the model we're training, which has parameters theta. So let's write down this KL divergence between the generative process and the one that starts at the target distribution and noises it. We can do that, and we can write down this KL divergence as a function of all of the noises that are introduced at each step of sampling the model. So this is like a reparameterization trick in VE training or in RL. And you can write the KL as a function of these noises, and then backpropagate to it. And this approach, it works. It has some issues, which is that it's hard to scale because you need to store the entire computation graph of the sampling the diffusion model for backpropagation. You have 1,000 steps, then you have 1,000 nested neural net evaluations. Also, it's a KL, so it has a mode-seeking behavior, and it has some local minimum. There are also related approaches which also work on the continuous time trajectories, which solve some associated partial differential equations, which I'll tell you about in a couple of slides. But there are other ways. So recall that the training a diffusion model requires approximating the score function of the target distribution convolved with different levels of Gaussian noise. So that means estimating the gradient of logarithm of this, this R as our target density convolved with Gaussian with variance VFT. So this opens the door to the use of different techniques in statistics for sampling, for hierarchical sampling, like importance sampling in SMC in the case of diffusion posteriors. These work. Of course, they have high variance and are hard to scale to high dimensions, but sometimes they do work. Just as an example of the kind of estimators you might use, some recent work has trained neural nets to regress to these Monte Carlo estimates. And there are different ones you can use. For instance, you can put the gradient on this term in the convolution. And then you can use this importance sampled estimate of the gradient of the log convolved density. And in fact, so you have expectation divided by expectation, and you can use a diagonal proposal. So use the same set of samples for numerator and denominator to make this more stable. And this yields a fairly good sampler for not too high dimensional problems. There are different estimators, for example, doing integration by parts to put the gradient on the normal instead of on the target density. So there are estimators like this, and various others exist, both for just sampling an unnormalized density and for sampling a posterior under a diffusion model prior. So we have the continuous time approaches, we have Monte Carlo. And then there are methods based on off-policy RL, which will be the main topic in the middle of the talk, because they're the closest to my heart, or maybe I should say to my mind. And this is the picture I showed also in the last talk, where we're going to treat a diffusion model as an agent, as a policy, where each action of the policy is performing one denoising step, and we're going to train this using a specific kind of reinforcement learning, such that at convergence we will get a model which samples the distribution we want. So again, just an example of the kind of objective that we might use in RL. If we have a trajectory tau, we want to make the forward likelihood proportional to the target density multiplied by the noising likelihood. So let's just enforce that directly by minimizing the squared log ratio between the two. So this is an off-policy RL objective in the sense that we want the two to be proportional, so related by a normalizing constant z theta, for every trajectory tau. And we can choose tau however we like, and this opens the question of exploration, like in RL and so on. We'll talk about this in more detail later. So different families of objectives to train a diffusion model without data. Let's go in a little more detail about the first couple. So diffusion models are stochastic differential equations. The noising process is a stochastic differential equation which is initialized at the target distribution and then follows usually some fixed dynamics. And the denoising process is another that starts with some prior distribution times 0 and follows some learned dynamics. That's mu left to right. That's the drift. And so we would like to find mu left to right so that the two differential equations are reverses of each other. So that way the prior distribution will be gradually transported to the target. So how are these two SEs related? We want them to be equal. So we should first write down the KL divergence. So to write down the KL divergence, we first need to get the density ratio, or rather Nikodym derivative. And you can write this out in discrete time, because both of them have Gaussian transitions on every step. And then you can take the limit, and this gives you what's called Gersanov theorem, also came up in the morning talk. It takes this form. So the density ratio between a forward and reverse process looks like this, which you see involves the ratio of the prior and target densities at the endpoints, and then these two stochastic integrals, which are sums of things that are integrals of things that are local in time. And then through a little bit of stochastic calculus, you can write down the KL divergence. So the KL divergence between the two processes also involves several terms. So it's first an expectation under the process P left to right. And it involves this term, which is local in time, so it's stochastic integral. And it involves the negative log target density at the point that we reach, xt, that big T, that should be x1. So this can be interpreted as a cost for an optimal control problem, in which the terminal cost, so when we reached the time x1, we get this terminal cost, we pay this terminal cost, and so remember that the energy is a negative log target density, so we want this to be as low as possible, and the intermediate or stepwise cost is this term here. So this way, finding the mu left to right, which reverses the p right to left, is the same as finding the solution to this optimal control problem, in which we have an intermediate cost, which tries to make the two processes equal, and then we have the terminal cost, which tries to make the target energy as low as possible. Now, there's also a partial differential equation perspective on this, which is fully local in time. So when do two stochastic differential equations, one forward in time, one reverse in time, define the same process? Well, first of all, they should at least agree in the marginal distribution at some time point, so boundary conditions. For example, the marginal distribution should equal the prior at time 0 or the target at time 1. The drift should be related by this identity, which also came up in the last talk. And they should satisfy Fokker-Planck equation, which is the condition that controls the evolution of the density pt under a given stochastic differential equation. Now, there are some notes. For example, Nelson's identity, together with Fokker-Planck for the forward process, implies Fokker-Planck for the backward process, just algebraically. So you need only one of those to be satisfied. But anyway, Two processes are reverses of each other if and only if these three are satisfied. So we have boundary condition, we have relation between the drifts, and we have relation between the drift and the evolution of the intermediate density. So another approach to training the drift could be to enforce these equations. So let's just fit models to approximate pt and mu left to right, and maybe we fix mu right to left, and let's try to make this satisfied. And there are approaches that work like this. Again, sometimes they work. Their main disadvantages are the sort of credit assignment issue, that you need to propagate the learning signal across very wide ranges of time when the objective is local in time, and the model may have a non-smooth dependence on t. Just to give a few key references on diffusion sampling in general before I go to more specialized diffusion samplers. We talked about KL minimization, so these are the key methods from papers from the more recent literature on the subject, which study does. Connections with SMC, optimal control, and so on are coming up in these recent works. And then the off-policy losses, which we'll go into whose depths we will, shall I say, go deeper soon, are those. And just a shameless plug of my own work on the topic, here are a few things to take a look at. So specifically reinforcement learning techniques to improve samplers, some unifying theory for discrete and continuous spaces, and study of the continuous time limit, and applications to large-scale problems. So we'll go deeper into these soon. Right, so that concludes the survey. So let's now talk about RL and diffusion sampling in discrete time. So first we need to review hierarchical variational inference, which is probably familiar to many. And we need to review entropy regularized reinforcement learning, probably also familiar to many, but we're going to put the two together. Right, so just recall, we're trying to sample a distribution where we only know its energy. So we want to sample a distribution whose density is proportional to the exponential of negative energy, and we want to do that by learning a dynamic transport of the measure from some prior to the target. So, for example, sampling the Z Gaussians by following such trajectories which may have been sampled from a trained model. And we're assuming a pair of SD is one left to right, one right to left. One generative, one destructive. So this is the picture I showed in the last talk. Here, initialize at the three colored points, here going left to right, and here's the intermediate density. If we make the two processes equal, then in particular, then at time one at the right endpoint they're equal, and so sampling the model left to right and evaluating at time one will give us samples from the target distribution. The push forward by the evaluation map at time one, if you like. So we were before matching the two processes through objectives coming from continuous time. And the discrete time version of this is actually the problem of hierarchical variational inference. So what's that? So in hierarchical variational inference, we assume a Markov chain with a sequence of variables x0 to x1 and so on up to x big T. And we're trying to approximate a distribution over xt by learning some parametric transition kernels from each xn to xn plus 1. So I'll use those interchangeably with their densities, those transition kernels, and denote them all by p left to right. So for p left to right to satisfy that the xt are distributed like the target, we need that p target is the integral over all these intermediate variables of the likelihood of following that chain left to right. Now, we can't directly enforce this equation because it involves this big integral on the right side. So what do? We introduce a variational distribution, which we call Q, or I guess here I've called it P right to left, which is a factorization of that same joint approximately in the opposite direction. And instead of trying to enforce that equality exactly, we try to make the two factorizations equal. So in hierarchical variational inference, we try to match the joint that starts at x0 sampled from the prior and then following the left-to-right transition kernel, and the p-target, what we're trying to sample, then sampled right to left using the reverse kernel. And then we have the data processing inequality for the KL, which tells us that the KL divergence between the marginal distribution at xt and the one that we want to sample is bounded above by the KL divergence between the two joints. Now, this should already look familiar to how the diffusion model was derived as a latent variable model on Monday. So we can solve the sampling of p target in t steps as a hierarchical variational inference problem. And if we make those transition kernels Gaussian, it's exactly training a diffusion. Now let's connect this to reinforcement learning. So in RL, we're not going to review all of RL, but just to review some setup, we're going to consider Markov decision processes which are deterministic and graded. So that means that we have an agent acting in a space, and that space, first of all, the action that an agent takes when it's at somewhere in the space, or state in the space, fully determines where it'll end up next. That's what deterministic means, as opposed to stochastic environments where there's some noise injected. And second, it's graded, meaning that the state space is broken up into these slices. So you started at maybe some abstract state as 0, and then you transition to the slice 1, and then slice 2, and so on until you finish. So for simplicity, we'll study processes like this. And what is a policy? A policy is a conditional distribution which says what action to take. So it's a function from each slice st to probability distributions over slice st plus 1. So for every state in a slice, you get a distribution over states in the following slice. So what's the goal? So if we're given a reward function, which is defined on transition, so when you transition from st to st plus 1, you receive some reward, then normally in RL we try to maximize the expected reward. So it's the expectation over sequences of states sampled from your policy, starting at the initial distribution and then taking many steps, of the total reward received. Now, because if our policies are unconstrained and the reward is deterministic, the solution may not be unique, but there's a deterministic maximizer. So always just transition. So just find one sequence of states that gives you the highest reward and just always follow it. So that's maybe not a very interesting problem. So to make this problem more interesting, we can add entropy regularization to it. So rather than trying to maximize expected reward, we want to maximize expected reward plus regularization parameter multiplied by the entropy of the policy. So entropy of the policy means entropy of the distribution over trajectories that the policy induces, or sum of expected entropies of transition distributions. And it's easy to show that the solution to the entropy regularized problem has the property that the likelihood of following a given sequence of states, x0 to xt, is proportional to the exponential of the total reward. This is an instance of scale-constrained optimization where this reward and the regulation term forces you to push up log likelihoods in proportion to reward. So sampling proportionally to total reward received along a trajectory is the same as solving the entropy regularized array. All right. So in the case of diffusion, we can define a state space exactly in that form. We have a sequence of intermediate values. We have Gaussian transition policies, and that's exactly our sequence of intermediate states sampled while sampling the diffusion model. And we can constrain our policies to be conditionally Gaussian when we are allowed to vary their mean and possibly the variance. Note that in general, it's not possible to perfectly sample proportionally to the total reward received along a trajectory using Gaussian policies. In particular, the reverse to a process with Gaussian increments is not necessarily Gaussian increments, but in continuous time limit, it all becomes fine. Okay, so now we should relate the RL problem to hierarchical variational inference. So recall that we have these two factorizations, so the generative and the variational posterior over a sequence of variables. And let's say that that these variables take values in the slice 0, these in slice 1, these in slice 2, and so on. So I'm going to define a reward in a very specific way. So we're going to initialize, so the agent will start at x0. We'll take regularization parameter 1, and we'll define the reward this way. So when you transition from state xt to xt plus 1, so slice st to slice st plus 1, you get a reward for the likelihood of following that transition backward under the posterior model. Except on the last step, where there's also an additional term, you also get a reward for the negative energy, so the log density of the target. So I will define the reward in this special way. And then the result is that the total reward for a trajectory is its total likelihood in reverse under the backward model, plus the negative energy at the final state. So the optimal policy satisfies that proportionality, because we know what the solution to entropy regularized RL problem looks like. So we can solve that hierarchical variational inference problem from the last slide by solving the entropy regularized RL problem. Now, note here that there's no assumption that all the state spaces are identical. A little more on this later. In fact, they could be discrete spaces, they can be different dimension, and so on. But in the particular case of diffusion, we can train a diffusion model to sample the distribution with the given energy by solving the RL problem. All right, so how do we actually solve the RL problem then? It's some optimization problem involving entropy of the policy and the final reward. Now, there exist many objectives in entropy regularized RL, but for the specific case of the RL problem we set up on the last slide, a few different ones exist. So there's a local objective, which is called soft Q learning. So we're going to learn this thing called value functions associated with all the states to enforce the soft Bellman equation. And if you've seen the basic form of RL, there's the Bellman equation, which replaces the logs of x here by max. And as you take regularization parameter to 0, that logs of x become the max. So you want to enforce that the value of a state is the logs of x of reward received for the transition plus value of the next state. This is a simplified form of a Bellman equation for a deterministic graded environment. And you have a boundary condition at the endpoint. Okay, so we can enforce that equation directly. And in the particular case of the rewards defined as we did for hierarchical variational inference, this has a simplified form. So first of all, the optimal policy will be proportional to the value of the next state plus the reward for transitioning to it. And under that identification, the Bellman equation transforms into this constraint, which says that the value has to be modified a little at the end, but the value of a state plus log likelihood of transitioning to the next state equals value of the next state plus log likelihood of transitioning backwards. And that's exactly the equation that tells you that the forward kernel and the backward kernel are in detailed balance with successive marginal densities. So the value functions actually recover the marginal densities of the factorized process up to a normalizing constant. Okay, so we have a local objective based on the Solf-Bellman equation, which actually is the same thing as detailed balance for a pair of kernels. Now, there are also global objectives. So you can iteratively kind of telescope the Solf-Bellman equation, and you can get these path-level objectives, which tell you that the value of the initial state plus log likelihood of a sequence of states left to right should equal the terminal log density plus log likelihood right to left. And as you can expect, the initial value then recovers the normalizing constant, and this does not involve any of those intermediate value functions or marginal densities. All right, so both of these can be turned into optimization objectives just by, say, taking left side minus right side squared and minimizing it on whatever states you see during training. So we've written down these objectives that when optimized for every state and every trajectory should solve the hierarchical variational inference problem. So how do we get those states for training? That's the question to consider next. So this is the objective we just wrote down. So this is the constraint that some normalizing constant plus log likelihood left to right equals terminal log density plus log likelihood right to left. So we can turn this into a loss by taking left side minus right side squared. Now, we don't know this normalizing constant. We could learn it Or we could just take a large batch and take variance, and then we cancel that term. So this leads to a so-called log variance loss, which has appeared in a few forms in the literature. So it defines a divergence between the forward process and the backward process. It's defined as the variance where the trajectories are sampled from some policy. So the divergence depends on that policy. It's the variance of the log ratio between the factorization left to right and the factorization right to left. So initialize at prior following the generative distribution, and initialize at the target and following the noising distribution. And we can use this divergence as a training objective, just by sampling a batch from the behavior policy and minimizing this variance. So how do you choose this behavior policy? Behavior policy is a term from RL, because we have an agent is deciding how to explore. That's how it behaves while it's learning. So how do we choose it? And that's the most interesting question. Well, one obvious thing is you could take the behavior policy to be the current diffusion model, the denoising model itself. So do on-policy sampling to get a batch of trajectories, do an update on this log variance divergence. And there's a theorem, it's hardly a theorem, it's a little bit of algebra, but it's been rediscovered many times. But it so happens that if the behavior policy is the left to right model being trained itself, then the gradient of log variance divergence is the same as the gradient of the KL up to constant. So if we do this, if we use this as a training objective on policy, it's the same as KL. Although it might have some advantages. For example, this doesn't require storing the full computation graph of the sampling, because we don't need to backpropagate through it. We just need to take our trajectories, compute this loss, and backpropagate to all of the terms in this log product, which breaks up into a sum. And so we don't have this nested, how do I say, we don't have the computation graph does not involve the nested evaluating the score-based model on the output of the last score-based model, and which is evaluated on the output of the last, and so on. All right, so we have this divergence, which on policy is just gradient of k. But we can do better than that. Because as we know, when we train models with reverse KL, we can get mode collapse. And we have no way to take advantage of interesting high-reward states, high-density target states that we may know. So we can do better than that. There are different ways. First of all, when we sample our diffusion model, we can be not on policy, but add a little extra variance to our kernels. So just be more exploratory. This is a common technique in reinforcement learning. You could maintain a replay buffer. So in RL, when you use a replay buffer, that means you have a queue of states that you have seen before. And instead of drawing trajectories for training from the policy, you draw them from the buffer, maybe prioritizing the more interesting ones somehow. And you can even take that replay buffer, which contains interesting terminal states, and you can update it offline using your favorite MCMC algorithm. And if the MCMC algorithm is good, then it will discover the high reward, the high density target states. And you can train on trajectories which are sampled by the noising process starting at them. Or you can even learn the behavior policy. So you can train another model which will attempt to sample trajectories where the sampler being trained has a high loss. So here's an example. For example, we're trying to sample this mixture of Gaussians. The diffusion model is missing these modes, and the exploratory behavior policy being learned wants to focus on those modes to train the main sampler better. So I have to show some results, yes. So yes, exploration methods work. So if you're sampling a grid of 25 Gaussians, if you just do on-policy sampling, you sample 6 modes and get stuck. If you add some variance when you're training, you discover some more. But if you use states found by MCMC to guide your sampling, you discover all of them. So the very, very inexpensive exploration running in the target space and the training of a diffusion sampler reinforce each other. Some other considerations, well, the exploration should be decayed over the course of training, so start out more exploratory and eventually switch to just training with reverse KL. Some quick connections with sequential Monte Carlo. for those who like that. I just want to point out that in the soft Q learning or detailed balance constraint, so the discrepancy between the left and right sides in that constraint is exactly the log importance weight that's accumulated when transition from one intermediate target density to the next following the kernel. So when you accumulate the importance weights in annual importance sampling, you're on each step adding exactly that discrepancy. So what this means is that training to minimize that discrepancy is actually training optimal twist functions and transition kernels to minimize the variance of logarithms of those importance weights. So if you go back and look carefully at the losses, then those local losses, the detailed balance or nested variational inference ones, are minimizing log importance weights of single transitions, and the full trajectory level ones from hierarchical variational inference minimize the variance of log importance weights for the entire trajectory. And in ongoing work, we're trying to combine this with replay buffer sampling, which we interpret as a kind of group importance sampling scheme, which seems to help exploration. All right, so we've just seen how to sample in discrete time with RL. While before I was telling you about how nice it is to think about continuous time objects with the associated PDEs and stochastic processes, because they're such nice associated theory. So why should we drop the continuous time assumption? Well, there are a few reasons. So the first one is that when we're trying to match two stochastic processes defined by forward and reverse SDEs, we are immediately forced to make the two diffusion coefficients the same. This is because the KL divergence between two SDEs with different diffusion coefficients is infinite. They're not absolutely continuous. Now, this is fine in continuous time, but in discrete time, when we're discretizing in time and sampling with a finite number of steps, that may not be optimal. So in fact, if you just relax that assumption and you learn a diffusion model in discrete time, and you learn the variances of the transition kernel in addition to the means, you can get better sampling with fewer steps. Now, notice that this consideration is completely absent in diffusion models trained from data, where we don't care about the step size when we estimate the score. We can just sample a single noise level, noise the data to that level, and then try to denoise. Here, the objective itself, which involves a product over the trajectory of the transition kernel densities, depends on what step size we choose. So if we have a small step size, we should learn the variances. And we can't do that in the continuous time interpretation, but we can with the RL. What else? We can even learn the reverse kernel, which is much more difficult in continuous time for similar reasons. And here's a recent experiment where this is the Niels funnel density. It's this distribution in 10 dimensions here projected, which has very high gradients near the bottleneck of the funnel neck of near the hole of the funnel. Yes, so a model which just uses a fixed number of steps and fixed variance has trouble modeling this node. As soon as you learn the variance, it gets better, and if you also learn the reverse process, even better. So RL with fixed small number of steps kind of requires this, and the objectives we showed before allow this. Also, this point of view allows an easy generalization to other kinds of kernels. For example, if we are no longer tied to the integration of the SDE by the Euler-Maruyama rule, we can make our kernels not Gaussian, but any distribution we like. Maybe mixtures of Gaussians, or if we're on a manifold, here's a work which did molecular dynamics using mixture of von Mises kernels on each step. So we can easily relax all these assumptions if we just think about discrete time in arbitrary kernels, as long as we can tractably sample each kernel and evaluate its density. And just to name a few more generalizations, all of the objectives I talked about work in discrete spaces, as long as we can define a destructive process. So I showed phylogenetic trees earlier. Here's an application to causal inference, where you sample a causal graph by adding one edge at a time, while the noising process removes one edge at a time. And exactly the same RL algorithm can be used to solve the same problem. So here actually we have a mix of discrete space, so edges, and continuous space, so parameters of the causal mechanisms in the final causal structure. So, in a sense, this kind of RL for hierarchical inference is a very universal RL for very universal algorithm that allows to sample unnormalized densities over spaces where the objects in the space can be constructed by sequential decision making. Not just diffusion, anything you can construct sequentially and parameterize a policy for. All right, maybe in the interest of time, I'll very quickly take you through the limiting properties. So we've seen the continuous time case, SDE and PDE. We've seen the discrete time case, which is RL, and detailed balance, kind of trying to make the SMC kernels and intermediate densities perfect. So it turns out that the two are actually related in the continuous time limit. So if we have an SDE, it can give us a policy, which is given by integrating the SDE. So taking the Euler-Maruyama steps, this is the picture I showed last time. And the more steps we take, the closer we get to the true continuous time stochastic process. So if we fix a time discretization, so the step size, we get a kernel, which transitions from time t to time ti to time ti plus 1. And we can use the discrete time objectives in that discretization, the RL objectives in that time discretization. So how are those objectives related to the continuous time objectives that we talked about at the start? Well, we take the limit as the time increment goes to 0. Well, the global objective, so the hierarchical variational inference objective on the time discretized thing, in fact just approaches the same divergence evaluated in continuous time. So this is essentially true because of some dominated convergence theorem applied to the fact that the Radon-Nikodym derivative between discrete time things approaches the one continuous time given by Gerson's theorem. So the global objectives in discrete time just approach the continuous time ones. And as for the local ones, it turns out that this discrepancy in detailed balance, which tells you how perfect your SMC transition kernel is with respect to the intermediate target, so you have to do an asymptotic expansion in the step size. And the first two asymptotic terms in the step size actually give you exactly the discrepancy in the satisfaction of Nelson's identity, which relates forward and backward drifts, and the Fokker-Planck equation. So as you take the continuous time limit, enforcing this detailed balance is the same as enforcing those conditions that make the forward and backward SDEs the same. So the implications of this are that you can train with one number of steps, train with one number of steps, say 2, 5, 10, and so on, but evaluate in continuous time with way more steps. But training is expensive, so you want to train with very few RL steps, short trajectories, and get results that are very similar to just training with a very large number of steps in the first place. Sorry that was fast. I just really wanted to get to this. So we've talked about diffusion sampling in the abstract, and now I suppose I'm not a statistician, so when I think about what to sample, it's always something from Bayesian machine learning or solving an inverse problem under a big generative model prior. And the algorithms I've talked about can be used for those purposes. So let's talk about that. So, well, first of all, I've shown you how to sample a distribution with an unnormalized density by training a diffusion model using RL, or by other methods. Now, what if we have a diffusion model prior and want to sample from the product of the density it defines with some likelihood function? So, for example, solving an inverse problem. Or taking a large pre-trained diffusion prior, say over images, and then taking an observation and trying to constrain by the observation likelihood and sample the posterior. Without training a whole new model on conditional samples from scratch. So here are some images of galaxies from the telescope. So this is the ground truth galaxy. Here's the noisy one. Here are posterior samples under a large diffusion model prior trained on galaxies. Here's a model of faces, which is then constrained to satisfy classifiers of different features. Here is deriving 3D meshes from a model, a caption condition model trained only on 2D. So all of these problems can be interpreted as sampling a posterior under a diffusion model prior. So this problem can be solved by basically the same methods as before. It involves just prenormalizing the base measure with respect to which all the kernels are defined, from just Gaussian with Lebesgue base measure to one that's associated with a prior diffusion model, and then basically the same RL algorithms apply. So you can just train a model to sample a posterior under diffusion prior rather than just a target density. So what can we do with this? Well, indeed, we could solve the problem I showed before. So we can take an unconditional image model together with a classifier and fine-tune it into a posterior model which samples the posterior distribution. What else can we do? Well, we can solve inverse problems, including nonlinear ones. So if we have a prior over what say images look like, and we have a way to evaluate the likelihood of a noisy observation given a sample, we can fine-tune that prior model into a posterior model that's conditioned on the observation, which samples the posterior. And that likelihood is not necessarily linear Gaussian. It can be anything you want that's tractable to evaluate. So, what do we show here? Deblurring, phase retrieval, and so on. There's that galaxy picture again. There are other applications. The same algorithms are applicable in discrete spaces, say for discrete diffusion models for text, for proteins. And recently there was a work that applied these ideas to black box Bayesian optimization, where you maintain a diffusion model which approximates a belief, and then in the presence of new evidence, you get a posterior distribution which you update by fine-tuning that prior to get a new posterior model, which then becomes the prior for the next iteration. So with the ability to just take a diffusion prior and fine-tune it to tilt the target distribution by an arbitrary function, we can iteratively perform the black box Bayesian optimization in this way. And then yet another application is performing inference in latent spaces of pre-trained models. So let's say that we have a prior over, for example, images, not a diffusion model, but something else. They're different families, VAE, generative adversarial network, normalizing flow. And we want to tilt the distribution by some likelihood function. So we can do that by training a diffusion model to sample in the latent space, which is usually much simpler and smoother than the target space into which that latent space is decoded by the model. So we will sample the prior in the latent space multiplied by the likelihood evaluated on the decoded sample. So here's that same picture I showed before, where we have faces and we have an attribute classifier. But here a diffusion model has been trained to sample the latent vector and receive a reward for the classifier evaluated on that latent vector that's been decoded. So we can do that with VAEs, GANs, with all sorts of applications, including images and protein structure. We can also do caption condition models, and this is the most fun picture I'll show. So this is, I think it's stable diffusion 3, which has some difficulty with compositional queries like cat and a dog, cat riding a llama. It can't do the relative position between the objects correctly. So you see pairs of cat-dog hybrids. What do you see in the prior? Strange thing. Cat-dog hybrid. The cat and the llama are in the wrong relative position. But if you have a reward model which is good at scoring or verifying whether a picture satisfies the prompt, whether the relationship is correct, then you can fine-tune the prior model to be consistent with the prior and also satisfy that reward. And then in the posterior that we obtain, we satisfy better the compositional specification while maintaining the same photorealistic or whatever qualities in the posterior. Right. Other extensions. Before we had considered sampling a target density starting at a Gaussian noise, but in some ongoing work we've extended this to the Schrödinger bridge case. So this is the canonical form of optimally transporting one measure to one distribution to another distribution. where both are available in the form of samples or in the form of densities. So such a problem has been solved before if you want to transport one data set of samples to another data set of samples. But if one or both are just available in the form of energy functions or densities, then it's harder, and you can use the same RL techniques to do that. So for example, here too, you're working in the latent space of VAE, which is trained on MNIST, just 10-dimensional, and you're transporting just all the latent vectors sampled from the prior to latent vectors which happen to be decoded to the digits 3, 4, and 5. And so digits that were 3, 4, or 5 stay very similar, while others are transformed to ones which are close to the original ones in the latent space, but are classified as the right digit. So now that we have around 10 minutes, let's draw some conclusions and take questions. There are a few open directions, so here are some things I'm thinking about. So I've already mentioned a couple of these. So Schrödinger bridges I've mentioned, and sequential Monte Carlo as a form of RL exploration strategy. Another direction is non-Markovian generation. So you can relax the assumption that we have this Markovian generation process in the target space, where each state lies in the target space, and introduce things like momentum, friction terms, and so on, or even these associated latent vectors with learned semantics, in the hope that you can do generation in fewer steps, or learn to better approximate the target. Another direction is trying to understand what happens with very few denoising steps, so very far from the continuous time limit, and show optimality of different parameterizations of the forward and reverse processes in this case. This is the subject of another ongoing work. As for the applications in Bayesian machine learning, which is probably the most interesting to those here. Now, if we have a good machine for sampling distributions over high-dimensional spaces, what should we do with that? Well, there are lots of high-dimensional inference problems in Bayesian machine learning, say parameters or Bayesian neural nets, or say kernel learning for GPs, as is shown in this picture. So we want to sample the posterior over parameters of some model from which we can compute a likelihood of data. Those posteriors are actually very, very multimodal and poorly approximated by simple variation approximation, so let's train diffusion models to do it. Another direction is in latent variable models, we can train diffusion models as encoders for getting low-dimensional representations of data. So what's shown here? So this is a clever dataset, which consists of renderings of little objects with different textures, shapes, and colors placed on a grid. And so these are actually reconstructions from a latent representation, which is really compact. It's a very low-dimensional representation. And it preserves the object structure. So it's a set of slots where each slot is supposed to represent one object. And you have to represent multimodality because there could be many representations of the same image due to occlusion. So here we fit a diffusion model to sample the latent representation given the input image, and then reconstruct it well. And then, of course, diffusion sampling in experimental design. I can't show you the finished example relevant to the subject of this workshop, for which I apologize. But I will tease this paper from a few years ago, which is about batch active learning. So if you have a GP, and you want to collect measurements at a batch of points to refine your belief about, to refine the posterior GP and refine your belief about the function. So the mutual information between the values at a collection of points xi, and the values at a set of query points, it follows a determinantal point process. And sampling proportionally to, say, the exponential of that mutual information times divided by temperature for a batch of a given size is generally intractable. So let's fit a model, which is actually trained by the RL techniques that I showed you before, to act as the acquisition policy. We train a model to sample a batch in proportion to, say, exponentiated mutual information with the thing we're trying to infer. And so we get an acquisition policy. This is the trained model here, which works better than simple heuristics, which tend to, say, mode collapse and take the entire batch from the same area, or just, of course, random points. Now, of course, this is just a toy example, and diffusion models can and should be used in Bayesian experimental design as well. This is just a summary of everything that's just been said. Okay, conclusion. So we've talked about how diffusion models can be trained, not given a data set, but to sample n a normalized density, or a posterior under a pre-trained diffusion prior. And this is closely connected to many other things in machine learning and statistics, SMC and annealed importance sampling, hierarchical variational inference, RL, stochastic control. So what can such techniques bring to Bayesian statistics? Well, of course, amortization. So where we can train models and sample in guaranteed finite time, or get proposals that approximate well. Exploration. So we can combine techniques that take advantage of generalizable structure in the distribution with ones that are effective at performing local search and which are very inexpensive to run. But on the other hand, what can diffusion-based sampling and statistical techniques bring to Bayesian ML? I think with all I've said, maybe the most interesting question is not how to improve the samplers, but what's the most interesting thing to sample? And what can we mine out of large pre-trained models, say, using the inference techniques that have been described? For example, can we ground world models used by agents in the knowledge stored in large pre-trained models by just interpreting that as posterior inference under the large pre-trained model prior? So all these directions should be studied, and I hope we'll see them answered with the distribution approximation powers of diffusion models applied to these hard Bayesian inference challenges. I think that's all I have to say, and I hope to hear many interesting questions or hear what applications you may have in mind. Before taking questions, I want to warn everyone that unfortunately I have to go and take a call immediately after answering them. So I can't talk in the coffee break, but at 4 o'clock I will be delighted to continue conversation.
Maybe a quick question at the back, Maria.
Could you please say something more about the connection between KL and control problem?
KL and control problem, oh, that was very far back, wasn't it?
3 or 4.
Slide 3 or 4, yes.
Because KL depends only on the initial answer.
The KL does not depend on the initial, well, the KL doesn't depend on anything. It's the KL between two processes. So there we go, yes? So it wouldn't make sense to speak of a KL between two trajectories because there are distributions over trajectories. But the KL between processes is an expectation over trajectories. And the function of the trajectory involves terms that depend on the start, on the end, and then integral over time for intermediate steps.
So what is the KL between?
It's the KL between two processes, where each process is a distribution over trajectories.
Okay. I thought it was just the initial answer, so that's why.
So, I mean, you can do KL disintegration, and this upper bounds, for example, the KL between the terminals.
One last question for Michael.
Thanks a lot for the presentation. So you have formulated you formulated as a reinforcement learning problem. So you defined or worked out what the rewards are, and then you could now tap into the whole literature of RL
Yes.
on how to solve the RL problem.
Yes.
I suppose now here you have used a particular objective like the var graph, it seems.
Well, there are a few can be used, yes. This is so in RL that's called path consistency learning.
Okay, so have you tried out other kind of algorithms, PPO, etc., etc.? How do they work? Or I guess multiple questions. Maybe you don't have time for all of them. Have you tried some other ones?
Yeah.
And can you say something how well they work compared to the one that you have used?
That's a good question. So we're in a little bit of a particular case because it's not just RL, it's entropy regularized RL.
Okay.
And so and you're in a deterministic environment. So many objectives just reduce to soft Q-learning and its relatives, like path consistency. So there are extensive comparisons of, say, soft Q-learning, path consistencies over short sub-trajectories, and the whole of our grid, which is path consistency over whole trajectories. At least for the kind of problems that we're able to solve without prior knowledge, the trajectory level ones seem to work best. Now, beyond the objective for a trajectory itself, there are also things like exploration techniques, the best way to use the replay buffer, and so on. And yes, there are lots of considerations about the best way to do that when training a diffusion.
Brilliant. I think in the interest of time, we'll thank Nikolay again.
Thank you.